on the board on the top left. Homework number 2 has been posted, and it's due a week from Monday. So you have a little more time. It's, I think, a little longer than usual. Definitely significantly longer than the first homework, so plan accordingly. And there was somebody was asking on Blackboard about the previous lecture. Only half of it was posted. The other half, the experts are working on it, so it is going to happen, I am assured, so it's a matter of a little more patience. Today we will be talking about post-buckling. We did a bunch of buckling solutions in the last 2 lectures, essentially, for plates, and now we will see what happens in life after buckling. And we have some introduction discussing some basic performance of post-buckled plates and comparing to post-buckled beams. We will then go through the real stuff, the nonlinear equations due to von Karman, which, if you can solve, you can actually get your post-buckle solutions. And in fact, we will do some of that for a special case, but not too special. I mean, in the sense that it's actually reasonably applicable to a bunch of situations. That's this one here. And then we'll discuss a little bit the implications of the results about how the skin behaves and what the loads are through the skin. To introduce this, we are going to watch a movie. And the movie is about a stiffened panel, a curved stiffened panel with 3 hat stiffeners, or omega stiffeners as you guys call them, which is tested under shear, and it's tested to go significantly beyond the buckling load. So you will clearly see the buckling load, and in fact you will see the half waves, and you will hear the half waves, those of you who have good ear. And then we will see what happens as you keep cycling. This is loaded. Okay, someone is right. It's the other way. I can't just do it randomly, right? They should be pointing the other direction. And you don't need to draw this. It's just for the discussion. Now, and this is loaded in fatigue, so it's a whole bunch of about 80,000 cycles in the end or something like that. You will see how it starts, pristine and nice, and you have a very well-defined buckling pattern, which is confined between the stiffeners. That's an extremely important point. Keep that in mind. You can buckle a panel as a whole, in which the stiffeners are part of the buckling shape, or you can have the stiffeners stiff enough such that they remain straight, and then they enforce some form of simple support or whatever. In this case, actually, it's more than simple support because they're hat stiffeners, such that only the skin in between the stiffeners buckles. And then after a lot of cycling, you will see this changing. And in fact, we'll also get to see the damage, and you also get to see some old friends of mine in this movie. And if I don't do it right, you will also get to see some ice hockey, but that's not on purpose. So let me switch to the PC, because that's the only place where I have this. Let me move on. Okay, this is the back side is what you see, and the other side, well, we'll go through this as it happens. This is Al, a very good friend of mine. The other guy's name I don't remember, but he was a reasonably good friend of mine also. You can see how big the, okay, why can't we hear? Okay, so you can see the half waves, which are all between the stiffeners. You can see the straight part here. And you can hear the buckling, and in fact you can hear different things happening because it starts buckling and then something else buckles. Also hard to see over there. Along this here is the highest stress location at the corners because you are essentially pinching the skin, and we'll talk about that much more. I mean, on this screen I can see it much better. But let's move a little bit. Where am I? Here. Yeah, you see this half wave here, it ends right at the corner where the stiffener meets the what is meant to be a frame. This is representing a frame. So those corners are the most highly loaded, and we will talk about those later on during the course. Now look at down here what happens. This is Jack with the camera. Jack is moving too fast, but we'll get to what I want to say in just a second. Okay, this is with the load on, so you can see the half waves, at least in this screen, not very well, but you can see them. And let me move now much later in the test. That's still the static residual strength test. It should be 540. Come on. Now this is after a lot of cycles, and I will show you where there is damage and how the buckling pattern has changed. First of all, let me back up a tiny amount. Yes, you see here, this is the web of the hat stiffener, and it has a crack that starts from approximately there and runs the full length up to there. So after buckling of the web, it actually cracked completely, and this was growing during cycling. We also had, if he goes at the right place, number 3 next to number, he moved, I can move back. Well, all right, I'll do it. Right here, there's a delamination, and right at the bottom corner, when it goes down at the bottom corner in just a second, there's a crack that's growing between the stiffener and the edge of the panel. Right here, there is a delamination and a crack growing. And now they're supposed to turn around to see the movie on the other side. First of all, you may notice how the sound has changed. There's a tiny sound first and then the big sound. I'm trying to find the other, here it is. Look at the buckling pattern now. There are a couple of them between the stiffeners, but this, what used to be confined in this bay has now extended, and you have two half waves very close to each other that go from here diagonally across below this stiffener and below the other stiffener. So basically the stiffener is no longer effective, and this is the ice hockey game. So originally, let me stop it. Originally, this was confined between the stiffeners, and then one of the edge stiffeners with a very big crack along its web, which makes its bending stiffness go down to 0, essentially, or very low compared to what it was, can no longer provide this simple support, and as a result, the buckling shape starts moving away, crosses this guy, because this one also has damage and delaminations at the bottom here, and comes all the way to the other end. And we will talk about what is preferable and what is not in a little bit. The message, of course, from this is that next time you are asked, you've been an aerospace engineer too long, if this is not a bottle of champagne opening, but the buckling sound of a panel. So, moving into the details now. This, I think, I'm pretty sure is the exact same panel, and you can see the buckle pattern before it extended beyond the stiffeners. So in general, buckling is not the end of the world. There is life after buckling, especially for plates. If you were to plot the applied load, let's say we have a situation of applied compression. This is a beam, that's why it's very narrow, and this is a plate. We're looking at them from the top. If you plot the applied load divided by the critical buckling load, then obviously you have no out-of-plane displacement. This is the out-of-plane displacement at the center on the horizontal axis. You have no out-of-plane displacement until there is buckling, so until the value is 1. Beyond 1, the beams would, for a very small increase in load beyond the buckling load, would show a very large deflection. And if you have very large deflection on a beam, you can imagine your bending stresses become very large. The bending moment is very large. So you can fail a beam very early beyond buckling load, typically. But a plate looks more like this. It doesn't have as big of an increase in the out-of-plane displacement as you increase the load beyond buckling. And therefore, the corresponding bending moments and strains are not that high, and you can actually have significant load-carrying ability. Now, for a conservative design, you most of the time don't allow anything beyond buckling, but for aggressive designs, you can do that. For example, the DC-10 was one of the first aircraft which on the vertical stabilizer had significantly post-buckled skins. And there are other designs out there, mostly on the military side, but a little bit are trying to find their way also in some civilian applications. The problem is that post-buckling opens up a whole new set of issues related to different types of failures that are not there or are not as pronounced below the buckling load. The biggest one is, if you imagine this is the skin and these are two stiffeners and it's buckled and this is coming towards us, but this one is moving away, that means that the region where the half wave is moving away from the viewer, there will be out-of-plane stresses that tend to separate the skin from the stiffener, so you can have skin-stiffener separation, which happens quite often. And in fact, there are the so-called anti-peel fasteners that people use in very aggressive designs where it's difficult to keep the skin onto the stiffener, and you put fasteners just to hold the skin there after buckling. It's not because you need them for any other reason. In addition, because of this buckling shape happening very often during a fatigue situation or cyclic loading situation, you can generate small cracks in the matrix, whether they are in between the skin and the stiffener or elsewhere, it doesn't matter. Typically it would be between skin and stiffener, but they can also be elsewhere throughout the laminate of the skin, for example. And those cracks during more loading will eventually become delaminations, or may eventually become delaminations and grow, and that leads to all kinds of problems. It's more pronounced at high post-buckling factors. High post-buckling factors means that your ultimate load is a high it's a number times your buckling load, and that number is high. So if the final ultimate load is many times larger than your buckling load, then you actually have significant out-of-plane deflections, and those during fatigue tend to be more critical than for lower post-buckling factors, obviously. So PB, post-buckling ratio, is the fraction of the failure load, the final failure load in the post-buckling regime, divided by the buckling load, not by the limit load. So you can buckle below limit load, which is a very aggressive design, or you can buckle at the limit load or higher than the limit load, but still below ultimate load. If you are trying to do a post-buckling design, the first most conservative approach that people will use is they will allow buckling at limit, and then you have a PB factor or ratio, I'm sorry, of 1.5 at ultimate. That means you only buckle, and beyond that you have 50% increase in the load before you allow final failure. That is conservative because typically you will never see the ultimate load in service, and it's only a way to save some weight. It becomes much more challenging, interesting, and exciting if you increase this beyond 1.5, so you allow buckling below limit load, and the lower you make the load, the more cyclic fatigue loads you will have that to survive during service. And as a rule of thumb, if you have a ratio of greater than 5, then you are really have an extremely challenging design. And it's very difficult to prove to yourself and everybody else that your design is safe, but it's been done. So a stiffened panel typically has some stiffeners, by definition, skin, and then there may be some frames or some kind of stronger beams at the edges. And let's say we're only dealing with compression for now. The question is, if you are trying to design this and you are going to allow buckling, what is it that you will allow to buckle first and what second, and why would you do that? You can buckle any part of this structure. So at first glance, at face value, it's not clear. Also, it's important to have a good understanding of what is the condition, let's say, of the stiffener being stuck onto the skin along the length of the stiffener. Is it really enforcing a zero displacement, zero rotation, both, something partial in between? And that affects your analysis. It also affects the performance of your design. Now, in fact, just looking at the picture, I can make this whole panel buckle as a whole with the stiffeners moving along with the panel. So all the stiffeners are doing, they're stiffening the skin, they're increasing the bending stiffness of the skin. So if you think in terms of the D matrix, the skin alone has a D11, D12, and so on. Let's say the one direction is along the length of the stiffeners, then adding stiffeners, it increases the D11 by how much we will see later on in future lectures. So that means your buckling load, which involves the D11 in that equation for buckling, would go up. That's one possibility. Another possibility is, as I was saying here, which is actually the desired possibility, I can tell you up front, is to make sure that the stiffeners have enough out-of-plane stiffness such that they remain straight as I increase the load until the skin between the stiffeners, and let's call them frames at the top and bottom, the skin between them will buckle. And you have a couple of options how you do that. If the stiffeners have also very high rotational stiffness, then the buckling shape, we will see in a little bit, the buckling shape is as if you have a skin that's clamped at the two sides with zero or near zero slope. If, on the other hand, you have stiffeners with low rotational stiffness, such as these guys, remember from second-year structures, open cross-sections have very low GJ, while closed cross-sections have very high, thousands of times greater. So in the case where it's an open cross-section, you will have a low rotational resistance, and therefore it's as if it would be simply supported with rotation being free at the edges of the skin. Then you can have just the skin, the stiffeners buckle. This is a really bad design if you make a stiffened panel and the first thing that buckles are the stiffeners in a column buckling 1/2 wave kind of situation. That means the main purpose of the stiffeners, which is to stiffen the structure, has been completely removed once they buckle, if the skin has not buckled already. Even one more possibility is that you locally buckle the stiffeners, and we'll do a lot of local buckling of stiffeners when we talk about stiffeners in future lectures. The desirable approach is to localize buckling, so make sure that it's in between the stiffeners and the frame in each bay. And once that happens, you can keep increasing the load, and then you can either locally buckle the stiffeners or locally fail the skin. That is much better than buckling the whole thing or failing in material strength first before you actually take advantage of the post-buckling capabilities. So skin buckling between the bays, stiffeners act as panel breakers, so that every 2 adjacent stiffeners and 2 adjacent frames, if you can buckle the skin there, that's the way to go in terms of getting the lightest weight, robust design. Robust in the sense that this local buckling, which is a failure, does not mean final failure of the entire structure. So you have some kind of tolerance to the first failure. So the skin between stiffeners and frames will buckle. The stiffeners do not buckle as a column. We don't want to column buckling, Euler buckling of the stiffeners. And ideally, we want them to stay straight. So if they stay straight, then we have an option to locally have 0 slope. So these are hat stiffeners, because being closed cross-sections, they have high GJ. And if they have sufficient high GJ, then under compression load, the buckling shape not only is confined between them, which stays straight, but also you have a local 0 slope or near 0 slope, and that means your buckling load is significantly higher compared to the case on the right, where the stiffeners now are open cross-sections, these L stiffeners, and all they can do is they give you 0 deflection. So at the points where the stiffeners are attached, you have no out-of-plane deflection, but the rotation is anything you want it to be. So you increase the load, you first buckle the skin between the stiffeners, then you fail the next thing that is the most benign, which would be a local buckling failure of the stiffener or a skin material failure, and that hopefully is at the required post-buckling ratio that you want to reach, which typically would be exactly your ultimate load, so that you have the most efficient design. So if we're going to do this and try to solve the problem, we need to do some math. I claim that the moment equilibrium equation and our FZ equilibrium is this one, and we have seen this before, so I'm not completely pulling it out of a hat. It's when we were talking about the this equation, which is one of the equilibrium equations for the shear forces, and through the shear moment relationships, which are the other 2 equilibrium equations, we can substitute the moments in here. Notice the out-of-plane loading here is the minus QZ. And we said that if there is non-zero in-plane loads, everything in the previous chart was pure bending. Now, if you have non-zero in-plane loads with NX, NY, and NXY present, then that equation that we just saw is modified to include these terms. So distributed load in the Z direction in the X and Y, but don't worry about those. And then in-plane, non-zero in-plane forces NX, NY, and NXY would give us this equation, which is essentially what we have here. These are the moments, and these are the NX and Y terms with the W, the out-of-plane displacement derivatives. Also, in general, I will have the PX, PY, and PZ. Now, those being distributed loads, I can neglect them for a pure buckling, post-buckling kind of problem. And I can invoke my moment curvature relationships. So the moments are related to kappa X, kappa Y, and kappa XY through the second derivatives of W. For convenience, I'm setting D16 and D26 equal to 0. And I impose a symmetric laminate, so the B matrix is 0. Therefore, my governing equation replacing the moments with the derivatives of the curvature with the curvatures, which involve derivatives of W, becomes this equation here. In fact, probably this is a little better. And it involves the W displacement in exactly the same form that we saw in the buckling problem. It involves distributed loads, which we are about to set to 0 anyway. And it involves, unfortunately, the NX, NXY, and NY terms, which are in-plane properties. In a pure bending case, I wouldn't have, in the right-hand side, these terms. In a pure stretching case, I wouldn't have W at all, which we will see in just a little bit. So the first so-called von Karman equation is this one, which is predominantly bending because the left-hand side is the pure bending problem, and it involves mostly the out-of-plane displacement W, which is associated with bending. But it involves stretching in the form of the in-plane loads NX, NXY, and NY. And to the extent that NX or NY or NXY can be written as functions of W, it's actually nonlinear. So as soon as you write this equation and the next one, the problem is nonlinear and very difficult to deal with in general. In terms of the second equation, we go back to our strain displacement. If you look at the top left here, I have epsilon x0, which is my mid-plane strain, is du dx, and that's the standard strain displacement equation for a linear system or small deflections. As soon as you allow larger deflections, you can show, and you can find it in the book if you want, that there's an additional term which involves the first derivative of W with respect to x squared. And immediately as you see that and this is squared, you know that this is a nonlinear term, and that kind of term will curse the rest of the derivation from now on. In a completely analogous way as the top left here, we have the epsilon y strain, which involves the standard term dv dy, but also again a nonlinear term. And of course, you would know that by now the shear strain would also have a nonlinear term, which is the cross product of dw dx times dw dy. Now, knowing what I want to arrive at in the end, I can take the first equation and differentiate it with respect to y twice to get whatever is at the top right. Take the second equation and differentiate it with respect to x twice, and I get what's in the middle here on the right. And finally, take the shear strain equation, differentiate it with respect to x and with respect to y to get this. If I add the first two and subtract the third, I will get a lot of the terms cancelling out, but unfortunately not all of them. I will get on the left-hand side second derivatives of the mid-plane strains, which is perfectly linear, but on the right-hand side I have leftover terms, the nonlinear terms that involve the square of the cross derivative of W and the product of the second derivatives of W. If I'm doing a small deflection problem, then the right-hand side is arbitrarily set, or can be neglected or set equal to 0, because these nonlinear terms would be small unless you have large deflections. So our compatibility equation that we saw in the previous lecture, and it had a 0 in the right-hand side, now it doesn't because it has these W terms, which mess up everything. Now I want to replace the strains with something that eventually will bring the displacements in and the NX, NY, and NXY forces. So I go to my standard NX, NY, and NXY relation with the relation to the strains, the mid-plane strains, and that means I need the A matrix. So NX is A11 epsilon x0 plus A12 epsilon y0. In general, there would be an A16 gamma xy0, but we are assuming the laminate is balanced, meaning for every plus theta there's a minus theta, and therefore A16 and A26 would be 0. So this becomes now our equivalent stress-strain relations, and we can solve, because these are three equations in three unknowns, the three strains, epsilon x0, epsilon y0, and gamma xy0. We can solve for those. It's just, as we said before, it's inverting the 2 by 2 A matrix here and so on. That's why you see at the denominator on the right-hand side here, A11, A22 minus A12 squared, which happens to be the determinant of the 2 by 2 matrix here. So I can determine epsilon x0, epsilon y0, and gamma xy0 as a function of only nx, ny, and xy, and the A matrix, which means I can take these now and substitute in this left-hand side, which involves the second derivatives of the strains. When I do that, I factor out the determinant here, and I get this whole expression on the left-hand side, which involves nx, ny, and nxy. And the right-hand side is unaffected, again, all these nonlinear, these two nonlinear terms with respect to w. And to show that there's continuity in the curriculum, in the second year structures, we talk about stress functions, at least in terms of the Prandtl stress function in torsion. In general, you can have stress functions for any kind of problem, not just for torsion. And we introduced the so-called Airy stress function. A gentleman called Airy was the first to suggest that aggressively for solving problems. It turns out, if you assume arbitrarily that nx, ny, and nxy are given by these expressions, where f is the stress function that we are looking for, then the equilibrium equations of the problem are satisfied exactly. Now, how do I know this? Because the equilibrium equations, typically written in terms of the forces, are in this form. Let me turn back the lights. Now that I found where the spots are, I will be playing with this all day. That way you can see the equations. Now, if you take the expressions shown here and you substitute, you will show that these are identically satisfied. The V is the potential of distributed loads. That is, if you have Px, Py, and Pz, that's where the V would be relating to those. But in our case, those are not present. We have only the in-plane compressive load or in-plane shear load, Nx, Ny, or Nxy. Therefore, those I can neglect, but using these expressions to replace my Nx, Y, Nx, and Ny, I will arrive at the second von Karman equation, which on the left-hand side has only the stress function F, the A matrix of the skin, and on the right-hand side has only the nonlinear terms with the W deflection. And this one is predominantly stretching or in-plane performance, because the left-hand side involves F, which is just Nx, Ny, and Nxy related to those, and only the A matrix. But it's only predominantly because the right-hand side involves the out-of-plane displacements, which are not stretching related, but more bending or out-of-plane deflection situation. So we have two equations and two unknowns, the W and the F. And if we can solve them, we can solve any post-buckling problem. So we'll do one example here. Are there any questions so far before I dive into solving this? Okay. So I have a square plate which is simply supported all around. That means the out-of-plane deflection is 0, but which also has some additional conditions for the in-plane displacements. As soon as you start talking about post-buckling, you have to really know what your plate does in plane also. If you think of a beam, what was originally a straight beam under compression goes into some kind of out-of-plane shape, and if these displacements are large enough, then you have a shortening, and it makes a big difference whether you are holding this edge completely flat, so it looks like this, or you are not holding it flat. There's a hinge here, so it looks like that. That would affect the shape, and the shape affects the local stresses and strains. In a complete analogy to that, we have to say what happens now at the edges as far as the in-plane displacements are concerned. And we impose arbitrarily that U, the displacement in the x direction, is 0 at x equals 0, which is the left edge of the plate. And V is 0 at the two horizontal edges, y equals 0 at the bottom and y equals a at the top. And we say that we are applying a constant force px in the following way. The force is applied through this very rigid beam that's pushing the plate, as a result of which a uniform deflection minus c, minus to indicate that it's compressive, is exerted at the edge x equals a. So there's a known px force, which actually, though, is distributed uniformly along the edge so that it forces a uniform displacement minus c, the value of which we don't know right now. What we do know is the applied px and the dimensions a, and we know the a matrix and the d matrix of our skin, and we have to solve the problem hoping for the best. So by now, when in doubt, we will assume something that involves signs. So the W displacement is an unknown constant W11 sine pi x over a sine pi y over a. Notice it's a in both cases because it's a square panel. If it were not square, let's say the y dimension had b, value of b, then it would be sine pi y over b. Also notice the subscript on W11 is 1 and 1 because I have sine of pi x and sine of pi y. If I had sine of 2 pi x and so on, I would have W21. So in general, this is the first term of an infinite series, a Fourier series. I mentioned this because later on I will show you the results also for the infinite Fourier series. Come on.
Are you assuming that the halfways, that there's one halfway in each direction?
Yes, in this case, by assuming only this, I am imposing only one half wave in each direction, and that's a very good point. Unless my D matrix has very weird ratios between D11, D22, and so on, then it's a very good assumption it will only buckle in one half wave. But there are cases where it might buckle in different half waves. If you remember our buckling problem for a simply supported rectangular plate, the buckling load was pi squared over a squared times d11 m squared plus 2 d12 plus 2 d66, the aspect ratio squared, plus d22 over m squared aspect ratio to the fourth. And I do admit it's the totally worthless thing to remember this equation. However, there is an m squared here and an m squared there, and last time we said if you differentiate this with respect to m, assuming it was a continuous variable, you would find the value of m for which you will get buckling, and that value was something like, and now I don't remember exactly, aspect ratio times d11 over d22 to the 1/4 or something along these lines. The point being that if I play around, assume even that aspect ratio equals 1 because this is a square plate. If this is a square plate, if I can make d22 ridiculously small compared to d11, I can make this greater than 1, greater than 2, maybe even greater than 3. As a result of which there will be cases, however peculiar they might be, for which this would be a totally wrong assumption because it will not be a one-half wave. In general, for most laminates used in practice, that would be a valid assumption, and the answer is only one half wave. Plus, the point of the example here is to see all the calculations, and then when you have nothing better to do at home, you can actually do the full infinite series solution. But in fact, I would have asked you to do it if it weren't for a master student that did it for me, which I will show you later on. But the point is very well taken. So, yes, please. What do you think?
Yeah.
Good. Yeah, I agree with you. You can look at it several different ways. If you don't check it and the assumption is wrong, you get the wrong results. If you don't check it and someone else does, then he gets more points. So on a utilitarian perspective, if you're going after the points, you have to think that way. From an engineering good design practice perspective, you have to be able to support everything you did in terms of the assumptions are valid and so on. Other questions so far? If our stress function is in this form, now, partly because I know that this works, and partly because it actually does make sense. Let's see why it makes sense. And of course, oh, there's the choke. We said, and I don't remember it by heart, that NX, okay, so this is my plate. It's under compression with the boundary conditions we just mentioned. So this is Px. And Nx is d2f dy squared. So if I go to my assumption to see if it makes any sense at all, I would expect that for this problem, the average force at any x location, so this is my x, remember, and this is my y. No matter where I am, if I calculate the average force, it had better be equal to this, because that's what I'm applying, and there's no shearing. Remember, there were all these, what do you call them, rollers, so there's no shearing to shed or transfer any load. So all the load coming in would be the same coming out. Therefore, the integral of nx dy must equal px, plus or minus, I guess minus because nx is positive and px is negative. So if I take that expression and I integrate, where's my pointer, you will notice that, no, I don't take that expression. I take that expression and first differentiate with respect to y twice. If I do that, the x dependence on the cosine 2 pi x, this disappears, and this one disappears. So you can see already that separating the x from the y dependence is very convenient, because that way I can calculate nx and not have to deal with the x dependence. In fact, I'm left with nx equals minus px over a minus 2 pi over a squared, all of it squared, cosine 2 pi y over a, and here there's a k 0,2 missing. So if I integrate now this, the average of nx dy, yeah, I think that's correct. So if I integrate now this, the cosine integrates to sine 2 pi y over a, and because it's evaluated from 0 to a, this term will disappear, so I will be left with minus px over a times y from 0 to a. The y is the integration of this term minus px over a. And obviously this is minus px, which comes back to this load, and this, what we did here, is independent of the x location. Therefore, while it's reasonably arbitrary, it actually makes perfect sense, because it reproduces the average force that we want, and it, if you check on now by integrating in the y direction, it will reproduce the py, which is the average force in the y direction. We don't know what that value is, but at least it's going to be a constant value based on the way the loads are applied, and so that one reproduces that also. So after all, there's some sense into this, and now we have unknowns, the py, the k20, k02, and w11, and we'll determine those after the break. Before doing more math, we'll look at the news. So if one starts using composites in cars, then everybody has to do the same thing, because if nothing else, the top of the line will sell just because you say it's composite, and then you have to be competitive. But also because if you do it right, you can save weight, which improves either your performance or your mileage and so on. So the latest to add to the continuing saga of composite cars now is Alfa Romeo, and they have essentially reached a deal with this company which will make the monocoque for the Alfa Romeo supercar, which is, I'm assuming, shown here. I'm assuming because I'm not having seen it. I don't know if someone just put a picture on the article that might be or might not be the right picture. So that part I don't know. So it will be produced in Italy, 3,500 cars per year, and only 1,000 go to the European markets. So it's interesting to try to find out who has the money these days in the world. And the two companies will invest in local production. They have also agreed to work together. Okay, this is all, it's actually good news, because the more automotive applications, the more the driving for reducing the cost will be there. So it will really help. It's not, the airplane industry is not as efficient in reducing costs as the automotive. Not that the automotive will be as robust and as well designed, and I say that with a little bit of care, but if a car breaks down, you just stop and wait for ANVB, whatever the guys are called, to come and help you, or you do it on your own. If an airplane breaks down, you don't stop anywhere effectively. That means you have extra factors of safety and so on. Plus the loads are orders of magnitude higher in an airplane than they are in an automobile. I had visited a big factory in the US, which at the time was making the first electric car. This is 1980 something, which I even drove, was kind of fun. And we were talking about the design and some of the aspects, and they were very excited to tell us that the highest load was about 3,000 pounds. 3,000 pounds is about 15 kilonewton, and that was not even a worthwhile load to worry about in an airplane of any kind. It's good loads start at 10 times that load, and then really high loads is about 100 times that load. Having said that, the automobile industry is actually quite efficient and quite effective in putting together new concepts. And this is promising, because between all these companies that will be applying composites, we hope to see some good things coming out on the manufacturing side, on the design concept side, and so on, some of which can be used in other industries, such as the airplane industry. Supercar weight to power ratio of less than 4 kilograms per horsepower, which I think is quite good. Carbon fiber composite represents 25% of the overall volume. Now, when you see it in terms of volume, you start getting suspicious. Why don't they do it in terms of weight? Obviously, there are other things that are heavy, and the percentage might go down. I really don't know. The main thing I want to talk about is the next page, I think. Yes. Sheet molding compound. I'm assuming you know what sheet molding compound. Anybody doesn't know what sheet molding compound is? Okay, in any case, yeah, okay. There's some couple of guys that are not afraid to admit. Yeah, if you take fibers and you cut them up in small pieces, small being in the 1 to 2 centimeter to a few centimeters length, and you mix them up randomly, and then you put resin, you create a part or a layer which has randomly distributed fibers in all directions, so it's quasi-isotropic. They are short fibers, which means each fiber along its length has a huge amount of strength, but at the end of that fiber, you have to transmit load to an adjacent fiber, which would be at a completely weird, different orientation through the matrix. So the strength of sheet molding compound is not good, but these are actually very good they're very low-cost material, and you can make relatively easily very strange shapes, because the fibers are extremely difficult to bend. A continuous fiber, and we will see that later on in the course, but this is a good opportunity to mention it. If I have a mold that looks like this and I have to put a layer of material in to conform to that mold, and the fiber runs along the length of this curvature, it will be extremely difficult to force the fiber to make a 90-degree angle or a near 90-degree angle there just by pushing. It just won't go. And in fact, if you have more than one layer trying to do that, in the end you will end up with separating them. It's almost impossible. But if you have short fibers, then it's very easy to do that because they are not as stiff that they tend to bridge. They are just much more accommodating. The stiffness is lower, and therefore it's more compliant. So they are using sheet molding compound, which is good. At the same time, it has a significant reduction in strength compared to any continuous fiber part. So they're taking a hit there, but it's good that they're saying resulting in a 20% weight reduction, and you see that and you say that's good, but it's over sheet steel. It's not over aluminum. So obviously, if you compare it to aluminum, it's not that impressive. And that's okay. I mean, that's what they wanted, and that's what they ended up with. Weight of 1.5 grams per cubic centimeter. The SMC is much lighter than steel, thank God. I mean, if it weren't. But look at this. This is about 1.5 to 7 is 6, 5, right? 5 times lower density, and yet all they end up with is only 20% weight reduction. So within an aerospace environment, this wouldn't be a very efficient design. If you have such a huge differential in density and all you end up with is only 20% weight reduction, then you are not doing very well. You are not taking advantage of the material capabilities, partly because I think, again, this sheet molding compound is not very strong compared to continuous long fibers, parts made with continuous long fibers. In addition, sheet molding compound, unlike aluminum, does not dent in the event of minor impacts. Now, this is almost irrelevant in the sense that composites under impact do not necessarily dent, but they delaminate, and they have more than a 50% reduction in strength for standard composites and composites like the sheet molding compound. So this is a very misleading statement in the sense that if you impact this, you may not see much of a dent or any other surface damage, but below the surface there's a huge amount of damage which completely compromises the strength of the part. And unless they have accounted for that, then they will have some very interesting surprises. Obviously, if you're making body panels, the load is very low in those guys. It's just aerodynamic load. So even if you impact it, you don't particularly care if your strength went to half its value because you leaned probably only 1/10 the value of the original. But that's a trade-off that one has to also take into account. Allows part integration, which reduces the number of components and leads to shorter assembly times. Remember, we said assembly is one of the killers in composites, and if you can minimize that, minimize the number of fasteners you use, and exactly that's what they're trying to do here. So they are lowering production cost by minimizing or eliminating or reducing the time, the assembly times. And then this is an interesting one because I just don't know what to make of it. Even the window glass was targeted. Okay, they had nothing else to save weight on, and they decided to actually reduce the window thickness 10% on the average. The windscreen, for example, is only 4 millimeters thick. All right, you want to be driving and there's a bird coming at you. You know, you're doing, this is a fast car, right? You're doing 200 on the Autobahn, and this bird is coming at you. You said, no problem, it's 4 millimeters thick. I hope they tested it and they are convinced that this works, but I would wait before I got in one of those at very high speeds. Okay, that's my story for this one, and we are going back to, if I can find it, more math. We assume the W and an F, and we substitute into the governing equations. Remember, we had those two von Karman equations, the second of which is shown here. The second has all these derivatives of F, fourth derivatives and second derivatives of F, and a whole bunch of derivatives on W. So if you substitute, the left-hand side becomes this, the right-hand side becomes that. Now you have to be very careful. Notice these are sine times sine. W has sine times sine. And all of a sudden here you only have cosine of twice the angle without anything as a function of x multiplying it, and a function of x here without anything multiplying it as a function of y. So that's because if I differentiate twice w, I will still get sine times sine. And the right-hand side of my governing equation here on the right involves second derivatives either multiplied with each other or squared. So now let's talk about this term, which is d2w dx squared, d2w dy squared. Differentiate with respect to x twice, I get sine times sine. Differentiate with respect to y twice, I still get sine times sine. So effectively what I have is sine times sine squared. And as you very well know from your trigonometry, sine squared of x is equal to 1 minus 2 cosine 2x, all this multiplied by 1/2. So I can actually translate my sine squares to cosine twice the angle. A very similar situation happens with d2w dx dy, but now I differentiate with respect to x once, the sine becomes cosine. I differentiate with respect to y once, the other sine becomes cosine. So I have cosine times cosine, which is squared. So now I have cosine squared of x times cosine squared y, and so on. But that one is equal to 1/2 1 plus 2 cosine 2x. So the same kind of logic guarantees, if you will, that I end up with linear terms in cosines. It would have been terrible if I would end up with sine square cosine or cosine square sine and so on. But because of the assumptions made here on the w, we end up with this. And now you will see that there are terms that are multiplied by cosine 2 pi y over a and terms multiplied by cosine 2 pi x over a. So I can individually match coefficients. And when you do that, you will solve for k02 and k20 as shown here at the bottom as a function of w11. So at this point, I still don't know my w11, but I have eliminated two of my major unknowns in terms of, and written them in terms of w11. Before proceeding, I have to do a little more exercise on because I need my py for reasons that will become obvious in just a little bit. I take my strain displacement equation that we saw that before when we did the compatibility a few slides ago, which has this nonlinear term with dw dx squared. And if I, and we also wrote before epsilon x0, where did we write this? Here at the bottom right, we have epsilon x0 in terms of nx and ny. So I have this expression for epsilon x0, and I know my nx in terms of the area stress function, d2f dy squared, d2f dx squared, and so on. I can take the nx in terms of the derivatives and substitute for epsilon x0 here, and then arbitrarily integrate over the entire domain. So basically, I take this relationship and I integrate over the entire plate from 0 to a with respect to x, from 0 to a with respect to y. Why do I do this? Because a whole bunch of interesting things will come out. On the what I have here is the epsilon x0 term, which is this, which is on the right-hand side. And at the very end, I have this minus 1/2 dw dx squared integrated because of this term here, which I brought over to the other side. Now, integral of du dx is just u. And because it's a definite integral from 0 to a, it's just u evaluated at a and u evaluated at 0. And then the integration with respect to y will just be an a multiplying everything, because integration with respect to y gives me y, because this integral du dx is a constant. Once I fix the limits of the integration, du dx becomes a constant. It's not a function of x, not a function of y. So the left-hand side is u at a. It's not completely, it's a function, it's not a function of x, I'm sorry, but it is a function of y. So it's ua of y minus u0 y times this a from the y integration. Now, at x equals 0, the displacement u by boundary conditions is 0. We said this edge is not moving, so this is 0. And at x equals a, we said this is minus c, which is my resulting uniform displacement as a result of the px load. The integrals on the right-hand side, if you carry them out, will be what is shown here, involving px and py, and the integral of w11 involves cosine pi x over a, sine pi y over a squared. Now cosine times sine, again from basic trigonometry, we know that sine of alpha plus beta is sine alpha cosine beta plus cosine alpha sine beta, and sine of alpha minus beta equals sine alpha cosine beta minus cosine alpha sine beta, from which, if I add them, these two terms will cancel out, and I get twice sine alpha cosine beta equals sine of alpha plus beta plus sine of alpha minus beta. So this cosine times sine is replaced, this cosine times sine is replaced with this divided by 2, which you can square and do the calculations. In the end, you get this. Once you have that, I can solve this equation for C and get an expression that relates C to the applied load Px and my still unknown Py and my still unknown W11. But now that I did this once, I can do it again. Instead of doing it for epsilon x0, I now take the epsilon y0, integrate with respect to x and y over the entire plate. And when I do that, I will find a relationship again for Py in terms of Px and W11. So the first integration of epsilon x0 gave me a relationship for C. The second one gave me a relationship for Py, which I can now substitute back there to get C as only a function of W11. Interestingly, if you look at this expression, its Py is Px times A12 over A11, and a term that involves W11. Now, if I have a isotropic material, A11 is equal to A22, and you can show that A12 over A22 is the Poisson's ratio of a plate. If it's isotropic, A22 equals A11, therefore A12 over A11 is the Poisson's ratio. So what this last equation is telling us is the following. If you did not have out-of-plane large deflections, W11 would be 0. Your transverse load would be the Poisson's ratio times the applied in-plane load, and that's exactly what you would expect. If you apply a unidirectional load and you confine the structure from moving in the other direction because of our boundary conditions, then the applied load in that direction would be just the Poisson's ratio times your applied load in the x direction. So this result makes sense. And now, remember our first von Karman equation, which had the left-hand side with the derivatives of W and the D matrix, and the right-hand side, which has the F's and W's. The F comes from nx. The right-hand side was nx d to W dx squared minus nxy and plus nxy d to W dx dy and so on. So if we use our definition for the air stress function to replace nx and nxy in terms of F, we will get that. Now, fourth derivative of W with respect to x is just this. You repeat our sine times sine term. The d to W dx squared, d to W dy squared is just the exact same term, again sine times sine. d2f dx squared, given our definition of f, is this which involves a cosine 2 pi x over a. d2f dy squared is this which involves cosine 2 pi y over a. Now that becomes a bit tricky, because once I will substitute here, I will say I need to match terms. Basically, I know I will have terms with sine times sine. On the left-hand side, in fact, every single term is multiplied by sine times sine. and that's great. On the right-hand side, unfortunately, d2f dy squared has a cosine 2 pi y over a multiplied by d2w dx squared, which has a sine times sine. So the right-hand side has one of the terms. The first term would involve a cosine 2 pi y over a times sine pi x over a sine pi y over a. So, and if you look at the other term, it will be even worse because it's cosine 2 pi x over a times the same quantity here. That would be for the last term there. However, if you now take this and this, which is a cosine times sine, and you use exactly what we have here, cosine times sine, it will be a sine of the sum and the sine of the difference. So this, the two parts, this is going to look like sine pi x over a times the, there's 1/2 from this guy, sine of the sum. So sine of the sum would be 2 pi plus, 2 pi y plus pi y is 3. So it's sine 3 pi y over a. But then the difference is 2 pi y minus pi y, which is sine pi y over a, just from this. So all of a sudden, my sine pi x over a and times sine pi y over a reappears, and that's wonderful. I'm still, unfortunately, left with a sine pi x over a sine 3 pi y over a, and there's nothing I can do about that. So what we do once we substitute here is we use all the trig, our trig to heaven approach to find all the sine pi x, sine pi y terms. Those are the first terms on this infinite series on W. That means what you have here, sine pi x times sine 3 pi y, is left over of what you would get if you had an infinite series. You would get additional terms, and you would be able then to match the sine pi x sine 3 pi y, or the sine 3 pi x sine pi y, which will also appear when you do the substitution. This means match coefficients of sine pi x a over a sine pi y over a only, because I have only one unknown right now, W11. If I had W12, W21, W22, and so on, I would have more terms that I would need to match. So when I do this, and I solve for W11, I will be satisfying my second von Karman equation approximately, because this equation here matches term by term for the sine pi x over a sine pi y over a, but does not match, or is not an equality when it comes to these terms, sine times sine 3 or sine 3 times sine type of terms. So this is where this becomes an approximation, because the other von Karman, the second von Karman equation, we satisfied exactly. But this one we can't. And we pay a penalty for this, but it's not as big as you might imagine. We substitute, and you will see that the one term is W11 cubed, multiplied by W11 cubed. The other is W11. I can cancel W11 because it's non-zero. I want the out-of-plane displacement. And then I will be left with one term that has W11 squared and another constant, so I can solve for W11, which, to make a long story short, becomes what we have here at the bottom. So this is quite significant because we managed to approximately, but still managed to solve the governing nonlinear equations and obtain this W11. And if I know this W11, I can substitute in my expressions for Py and get the transverse load. I can substitute for C to find my displacement. I can substitute for K20 and K02 to get the F, and from the F get my NX and Y and NXY and so on. So in principle, I have everything that I need. Looking at this expression, this is a square root of something. First of all, that something had better be positive. The square root of negative in a buckling problem it's a no-no. It's definitely, you will agree with me, the numerator on the left here is positive. Anything that involves A11, A22 times that D matrix is positive. And you can show that for any material, in fact, the proof is not very straightforward. It has to do something with positive definiteness of the energy of the system. For any material, A11, A22 minus A12 squared would be positive. So everything to the left of this bracket is positive. On the right-hand side, on the rest of the expression, I'm sorry, the right-hand side of that expression, I have my applied load Px, and then the denominator, which you can see that it's all positive, and I'm subtracting 1. There's no guarantee that the part to the left of this minus 1, this fraction, will always be positive. In fact, it's not. You have to make your applied load Px greater than this denominator, such that this fraction is greater than 1. I mean, it's obvious, but all of a sudden it starts making sense, because you can show that this denominator happens to be the buckling load of a square plate with the boundary conditions that we just imposed. So if I call this denominator the critical, Px over P critical must be greater than 1, otherwise I have no solution. Or essentially, I have a case where W11 does not exist and I have only in-plane deformations. So if my load Px is below the buckling load, then W1 does not exist. If it's above the buckling load, then I get a solution. And let's see what the solution looks like. We have an example. 3 plies of fabric material, square plate. Properties are given here just for completeness. This is my applied load P divided by P critical. And this is my center deflection divided by the thickness. So W11 actually is the center deflection for the assumption of W11 sine pi x over A sine pi y over A. Obviously, W11 is the midplane deflection divided by H to normalize it. If my applied load P is less than the critical, the buckling load, so if the ratio is less than 1, I get nothing. And then after 1, I get my out-of-plane deflection shown here. More interesting is if I now calculate my nx. Remember, my nx was, I erased it, d2f dy squared. So I know my f stress function. I can substitute and calculate nx and even normalize it by P critical over A. So this is my buckling load divided by the width of the plate to make it into the same units of force per unit width. And if I plot it as a function of y over A. So remember, this is the situation. This is x, this is y. I apply a px, and it's held here. Nx is in this direction, horizontal direction. Therefore, at any location, I can plot the nx as a function of y, which means it would show us how nx changes from the bottom edge to the top edge of that square. And if my applied load is equal to the buckling load, then nx is constant. Throughout the width, nx is constant, which is, everybody knows, if I apply a load in a plate and it's not buckling, the load is constant as a function of the transverse coordinate y. As soon as I go above buckling load, though, that makes it extremely challenging and interesting. Then the nx is no longer constant, and it doesn't take much. Let's say at P over P critical is 2 or even 5, you will see that all the load goes at the edges. This nx, this px load causes an nx distribution where almost all the load, or most of the load, goes at the edges. The center of the plate, because it has buckled, it cannot really carry much load. Think of it in terms of a beam at the center, which once it buckles, we said will just deflect like crazy, and therefore it doesn't have enough stiffness to support the load. Think in terms of finite elements or situations, the two edges, top and bottom, are constrained, and they are therefore very stiff. So if I apply a load, the load will follow the stiffest path, so it will go to the edges. And this solution tells us exactly that. It also allows us to do an approximation now. If the edges have such a high load, then maybe I can neglect what happens at the center, and approximate this in the post-buckling by having two regions of constant force at the edges and nothing in the middle. If I can do that conservatively, such that this load here is at least equal to my applied load, and such that the fact that there is no load here is still conservative, then I will have an easy way to approximate this problem. And all I need is to determine now this width, the so-called effective width or effective skin. In a post-buckle under compression situation, there is only a portion of the skin that really carries load at the edges. The question is, what is that portion? So to find that, we basically say we take our NX distribution, find the highest value, which is this one, NX maximum, and assume that this goes across over a certain distance such that the area under these rectangles is equal to the area of the entire NX over the width. So if I take NX and integrate with respect to Y, and this is the NX, the real NX, if I equate that to this NX max times the B effective width twice for the two edges, I can back calculate my B effective, because the NX max is the maximum value which I know. So, going back to my definition of NX in terms of the stress function, is the second derivative with respect to Y. So, if I substitute for F, I will get this expression for NX. If I just look at it, my NX maximum is given by this quantity. So, this is what goes on the right-hand side. Also, if I take this and I integrate NX with respect to dy, I find minus px. Now we know that that's correct, because we said all along earlier that our assumption for F must be such that it reproduces the average force. And essentially when I integrate, I'm reproducing the average force. So minus px, and this one is 2 NX max B effective, so I can now substitute, I can now substitute for my W11 for the NX max, and I will finally find that my B effective is this expression here, which involves the A matrix, involves the buckling load, and involves the applied load Px. Now, if I have a quasi-isotropic layup, A12 over A11, I said, is the same as A12 over A22, which is the Poisson's ratio, and the A11 over A11 plus 3A22 is 1/4. Because A11 is equal to A22. So this is 1/4. Therefore, Poisson's ratio, and the Poisson's ratio is 0.3, which means for an isotropic material or a quasi-isotropic layup, my B effective is A, which is the width of the plate, times this, which is a function of the buckling load and the applied load. So, and this holds also for metals. There's nothing in the derivation that's particular to composites here. If I make my applied load Px much, much larger than the P critical, then this quantity in the parentheses on the right here is 0. So I am left with B effective equals 1 divided by 3.3, which is 0.303 times A. So for a quasi-isotropic layup, I would have the width of this to be 30%, plus 30% is 60% of the width. I'm left with 40% of ineffective length or ineffective width of the plate. This is for quasi-isotropic or isotropic materials. If you try to generalize for anisotropic plates, basically we have this variable A12 over A11, and this, from this expression, we have A12 over A11 and A11 and A22. So if you put in typical values, A12 over A11 never ranges outside this 0.05 to 0.7. You can calculate for different P critical over Px the B effective as a function of A. So you will show that there is a very narrow range for a given A11 and A22. There is a very narrow range where B effective would be. If you change A11 and A22, then this bunch of curves will shift up or down accordingly. But the bottom line is this B effective is relatively independent of the laminate. Once you pick A11 and A22, this ratio is not that, even if you vary it over a wide range, it does not give you much of a variation for the B effective shown on the y-axis here. Now, we have 10 minutes. Do you want to talk about homework or do that on Monday? Or I have about 4 more slides and we do the homework on Monday. What do you want? Homework now or briefly or Monday? Yeah, as if you were going to do the homework on the weekend. All right. Okay, then tomorrow you will send me an email with what you've done so far so that we can double check it. All right, so we'll stop here and we'll continue on Monday. And let me bring up the homework. Way at the back, can you see or should I make it bigger? Bigger. Okay, it's on buckling and post-buckling. A rectangular composite panel is under compression. The panel is simply supported all around. So you have the boundary conditions, you have the applied load. And the width of the panel is 20 centimeters. So you have a situation where the load is applied. This is 20 centimeters. And the length can be variable from 10 centimeters to 1 meter. So the maximum can be 1 meter, but the minimum can be 10 centimeters. So your aspect ratio obviously is varying drastically. And the layup has 8 plies, and those 8 plies only use 0, 90, 45, or minus 45. You can combine them any way you want, as long as you have a balanced laminate, total of 8 plies, and you satisfy the so-called 10% rule. The 10% rule, which we will see later on in the course more, says that you have at least 10% of the fibers in each of the 4 principal directions, the 0, 90, 45, and minus 45. At least, that means if you had something with 100 plies, then 10, you need at least 10 zeros, at least 10 45s, 10 minus 45s, and 10 90s. That's 40, so you have 60 left. So those 60 could be anything else. In this case, because it's only 8 plies, it's much more constrained, and that's good because otherwise you would be checking too many cases. You are supposed to find the best layup out of all the possible combinations and the corresponding buckling load. As you do that, you're supposed to assume D16 and D26 is 0. Some of your possibilities, given with these constraints, will have D16 and D26 significantly different than 0. Some of them, the D16 and D26 will be quite small, but I want you to assume across the board that D16 and D26 is 0 so that the equations, the simpler equations are valid and you don't have to do something else to find buckling load when D16 and D26 is non-zero, which is very difficult to do, by the way. So I want you to plot buckling load versus length. So as the length changes, you will tell me it's going this way or it's going that way as a function of length. By the way, anybody that finds this should go back to high school, but in any case, as a hint, I'm helping you now. The material properties are given, and then, okay, you found this curve, which definitely does not look like this. Is this a design curve? By design curve, I mean, can you then tell the guy that as long as it's 20 by any length, just read off my curve. Let's say your length was 0.5 meters. Could you read here and read the value and say this is the buckling load at which the panel fails or not? Now, the simple answer to that, that's why I have the parentheses following, is that no, it's not, because you have to account for material scatter, environmental effects, and damage, and knock it down. Well, forget about this and now answer the question again. So let's see who is thinking on their toes here. Any questions on this so far? Yes, please.
You say the 10% rule was 10% in at least all of the 4 directions you mentioned?
Yeah, 10% in the 0, at least 10% in the 0, at least 10% in the 45, 10% in the minus 45, 10% in the 90. But because it has to be symmetric, then, and it's 8 plies, and so on. Now, okay, you did this, so by now you have the results. Now you have to do the same thing, but now the sides are all clamped. So there will be a different curve, and you are supposed to plot it on the same one. So let's say the clamped is here. And if you get this, you have to go back to high school. But this is the simply supported. So there will be 2 curves. Assume now that the best layup, whatever you found for part 1A, the simply supported case, you use it to make 0.5 meters by 0.5 meters. Yes, I know that this width is not the same as the 20 here, but that's done on purpose. You take that layup, you make a square under compression with these boundary conditions. Now it becomes a post-buckling problem. And suppose that the panel is to be designed for a certain post-buckling factor, post-buckling ratio. I want you first to make a cut along at the center here, along y equals a over 2. I'm sorry, y is going in this direction. If y is going in this direction, you make a cut here in the middle, y equals a over 2. And determine what moments you have mx, my, mxy. You find those moments and give me the analytical expressions at those locations. Now, the only reason we're doing this is because I want to determine a stiffener here and here with a given GJ and find what GJ I need to make this be as if it were a clamped plate instead of a simply supported plate. So, step by step, you calculate the total moment along the edge y equals a over 2 by integrating whatever you found on the previous part. You found some moments, you integrate them along y, and you find the total moment. You also calculate the maximum rotation of the panel along that edge here. That comes all from your solution to part A. You know, if you have compression and it's post-buckled, you can find the exact shapes because we know W and so on. So you find the maximum rotation, and now it gets confusing, but it's not. If that maximum rotation is caused by the moments in the previous part, then if now the panel were clamped, that rotation would be 0. Basically what we are saying is, if I look at my panel, this is half the panel. And there are some moments here. This is my torsion thing, and the other moment there, and whatever moments there are. And this is the deflected shape, let's say. If this is deflected, then because this is not moving, remember W is 0 at this edge, if I were to plot it, it would look something like this, let's say, the deflection. So if I draw a horizontal line here, I will have a certain angle. That's the angle you're supposed to calculate at this location, and to assume that this comes because of this total moment that you integrated along the edge. And then determine what should be the GJ of a stiffener that you can put at this edge, such that this rotation is this angle now becomes 1% of the value you calculated. What do I mean? I mean that suppose now, instead of the plate, I have a monster stiffener here. And if I ever learn to draw, this stiffener, under this bending moment, torsion, whatever it is you will find, will twist. Now we are to assume that this edge of the stiffener is clamped, that edge of the stiffener is clamped. So I am applying this load, the total moment I calculated, on a stiffener which has a certain GJ. What should that GJ be such that the rotation of this stiffener here is 1% of the angle that you calculated when there is no stiffener? In that case, if it's only 1%, you can effectively assume and expect that that stiffener has enough GJ to impose a clamped type of boundary condition because the angle here is very close to 0. So this gives an idea of the requirements for stiffeners to be placed all around the panel. Given your answer in problem 2 for 0.5 meter by 0.5 meter, okay, now you found the GJ, and you're going to guess what that stiffener looks like. So it's all free to you guys to decide what's the cross-section, what's the thickness, and so on. And you have one stiffener here, one stiffener at the other end. And those have a certain weight based on your design for the given GJ. So if they have a certain weight, and you actually generated a plot for the simply supported, and obviously the clamp is above it. For 0.5 and 0.5 dimension, you will have a certain difference in increase in buckling load between simply supported and clamp. That's what you found before. Now, that difference is 1%, 100%, 400%, I don't know, you determine it. Is this difference worth the increase in weight? By what percentage are you increasing the weight of the plate? And by what percentage are you increasing correspondingly the buckling load? I mean, the buckling load. Is it therefore worthwhile or not? Question.
Are these stiffeners also subject to the 10% rule?
No, I will accept, because we haven't said anything about stiffeners, we will accept anything. They cannot even be unsymmetric if you want, I don't care. Because I don't think, I mean, if you impose some conditions, the weight goes up in the stiffeners. But that in and of itself will not kill the concept. I mean, either you will immediately see that, oh yeah, no problem, because no matter what I do to the stiffeners, I'm only increasing the weight by 1% while I'm increasing the buckling load by a factor of 4. But if it's the other way around, you are increasing the buckling load by 1% and you're increasing the weight by a factor of 4. No matter what conditions you impose on them, it just gets worse. Other questions? Monchil. What x equals y equals 0? This one. W equals 0 at x equals y equals 0 and x equals y equals a. So along the edges. The full edges. Isn't this what it says? If x equals 0, which is this edge. If x equals a, yeah, no, that's fine. Other questions? Going once? David. Yeah, you had better have taken the second year structures and learned something out of it, because you give me the wrong shape, even if it works, you in particular, for 10,000 reasons I will crucify you. You're a TA on that course, so you better do it right. Other questions? Okay, we'll see you Monday then.